Okay, I'm just going to start it off really quickly. We created fission and fusion. These are the two particles, the smallest ones that exist, and they are light. And normally they are glued together so tightly that you can't break them apart. However, we did break those apart. These are fused together. Now, what did we do? We put them through a venturi, which is right here. This is the particle that's in this stream right here. When it hit the venturi, this is what happened. The black separated from the white. That's fission, and when they came back together, that's fusion. I think we can use this to get free energy, and I will explain in extreme detail, so stick around. Okay, my outstanding friends, Roger once again. Today we're going to be talking about the new physics they're looking into based on light acceleration, which we have been doing for a number of years. They're starting to look into it finally. And this is another one. Physics defying quasi-particles could open a whole new world of microscopy. That's what we did, was we did physics defying particles. There are tiny particles made from light, not from protons, made from light. So this is a different realm. It's a little realm below what they're doing at CERN and Fermilab and all those places. They're working with big heavy protons. We're working with light. But we did create this physics defying particle soup. And I will show you, and it's not a soup, it's a very well defined particle shown interacting in a very defined manner under very defined circumstances. That's the key. You put these together, you got fission, then you got fusion. Now, in the light realm, so we're in the light photon realm, which is only one little particle at a time. We're not breaking big, huge chunks. In other words, if you looked at this, all right, if you looked at that and said that's a proton, and when you smash two of those together, all of these particles go flying. You can get chunks like that. That's going to hurt you. That can really damage you. That's why radioactivity is so damaging. And then it also interacts with your molecules and snaps and fractures them when it tries to engage with the other molecules that it comes in contact with. It's an unnatural state of the particle. So it tries to get stability by cracking into something or breaking apart and throwing off chunks. That's what radioactivity is. It works both ways. Now, what we did was we worked with light. So we're down here. We're right down there. Because the protons are made out of dipoles, which are light. And I can show all of this very clearly. And let's go right into it now. Because, like I say, they're starting to pay attention. And I've got a bunch of articles here that have just come out within the last couple of days. Because I've really been pushing this hard. And I am going to continue to push it hard until somebody like Elon Musk or somebody that wants to do something contacts me, or at least starts to move into this. I can see they are moving into it, but they're talking to as a novelty, basically, not for energy productions, which I think we could have a portable, handheld energy production device that you could work around, and it would be absolutely free energy, 100% free. Because we can separate the white from the black particles, which is, they're talking about a whole new quasi-particle world. Yes. They've never seen it before. They don't understand it, and they still don't understand it. So let's see if we can understand it. All right, let's just start out with the definition of fission and fusion. What is the difference? Well, fission means to break something apart, and fusion means to bring it back together. So what does that mean in the atomic realm? Well, here's what it means. It says all of the energy we produce comes from basic chemical and physical processes. Basically, it's burning and that type of thing, and chemicals reacting with each other to give off energy, which is electrons. It's mostly been accomplished throughout history by burning carbon-based material like wood, coal, gas, and by harnessing power from the sun, wind, and the water, which is electrons. Now, listen to this. Fission and fusion are two physical processes that produce massive amounts of energy from atoms. Massive amounts of energy from atoms. Well, we are in the subatomic realm. So they are working with protons, like protons and neutrons, which are big, gigantic things. They are actually made out of these. That's actually what these are made of. They don't realize it. They can't understand that. Because when they have, I'm working with light. So here's what I'm working with right here. Two of these together, actually, because they're two dipoles, back to back. All right, they're just like that. They're two. There's a black and a white and a black and a white, as I show you, and I will many, many, many times. That's what light is, and it has a big magnetic field that surrounds it, and I mean huge, huge. If you look up hydrogen, hydrogen is only one proton, one. It has a 21 centimeter wavelength. So as far as I'm concerned, it regulates 21 centimeters out. It still has a magnetic influence. 21 centimeters out from a proton. That's the way I'm looking at it. That's its wavelength. So it has to be able to influence something 21 centimeters away. You see this? Fission and fusion, two physical processes, produce massive amounts of energy from atoms. They yield millions of times more energy than other sources by using nuclear reactions. Well, a nucleus is like protons and neutrons. They're in the nucleus. Well, they're made out of these, so we're using the same stuff, only we're using a smaller bit than these. So maybe they get a lot more energy because they just have a bigger particle. It doesn't matter, because we can do this all day long, squirt these through, and you should be able to carry those around in a little lunch box like that. If all this stuff works that I'm talking about, and they're talking millions of times more energy than from other sources, and I can show you right now, it is creating one hell of a lot of energy, and it's separating the electrons, completely separated from the muons. So don't forget, millions of times more energy. And what are we working with? Fission and fusion. Fission means you have to break something apart. Fusion means it comes back together. Can I show that? I absolutely can. This right here, my friends, is light being accelerated. Not supposed to happen. It's accelerating from that wave. They say, oh, it mimics acceleration. No, it isn't. It is actually accelerating. And it hits here and divides, creating fission here and fusion here. The particle right here is this particle. Where are you? Here you are. It's this particle right here. And it's fused together. That's fused together. That's what a photon looks like. Now they know at Fermilab, they have seen these in CERN, they've seen the black and the glowy parts, but they just see them in debris. We have them right here as its actual photon self. And that's what they are, they're glued together. Now, as it goes through the air, it's banging into every other particle's field. That's why this glow is bigger than that, because that one's not banging. It's being protected by the dark matter that's in front of it. And this is dark matter. That's all it is. And it's a muon, never changes, a fixed particle. And that's what they call it, fixed particle and a point particle. The point one can get big and small and squish down and do all kinds of things. The other one is just like a bowling ball, never changes, never, ever, ever, ever changes. And this is what happens as the photon. Now, if we could break that apart, that's fission. If it comes back together, that's fusion. Well, guess what? It does both of those things all by its little self when you put it through a Venturi. All right, they can call this quasi-mimicking acceleration. I call it acceleration. And a Venturi accelerates and atomizes gases and fluids, and this is nothing more. Light is nothing more than a fluid. It's these little particles, and when you pack them together like this, it's like a hose coming down here, and when it can't get through, it accelerates. And the black can't get through, you get fission here, and you get fusion back here. The fusion just happens automatically. The black just can't get through, and it can only squirt the white through. And I'm going to show you this in extreme detail. First, let's look at the particle itself. All right, here's the particle itself. Coming down. gaining energy, turning into a photon, and here exploding and bouncing all these white fields coming back from this. All right, so that's the actual particle, which I just showed you a minute ago. All right, so this is the particle in the wave accelerating. Bang, it hits here. Until it hits here, it's this particle. It's this particle right here. Until it hits the Venturi, and then it separates. And the separation is right here. The black surrounds here, but only the white is allowed through because of the tuning of the Venturi. And then when it comes back together here, that's fusion. So fission, fusion. Now, very close up is here. I showed you the black ball. The black stays this way and squirts the white right through. Just squirts it right through. And eventually over here it recombines and turns back into light particles as the Higgs fields develop. The Higgs fields are what create the particles back to being particles of light. Before, they're just sterile muon and electron shower, and that's exactly what they say again at CERN, and I'll defer to them. They say a muon neutrino, electron neutrino tied together turn into a muon, a solid muon, sterile, and an electron shower. And that's precisely what you see here. It's exactly what it is. I showed you when they were together. That's fission. You know, I don't care how anybody looks at it. There's no way to look at it any other different. It's fission. They broke apart, and they come back together here. I know they do. And that's fusion. So fission, fusion. This is raw energy. We should be able to harvest that and put it in a little box like this, and this should be able to run your house. You see what they said? Millions of times more energy. Millions if you can do this fission. Now, we're using light, so we would have to maybe have thousands of lasers inside that box, but you could actually do that. These are so small. These are pinpoint. And they actually are claiming that now, that yes, this is true. Hold on, where is it? Well, this is one of them. This is the other one right here. Look, tiniest particle accelerator, so small it could fit into a pen tip. You put 1,000 of them in here, and just think of the energy you could put out. I'm not positive you're going to get what I'm saying, but I'm pretty sure it looks pretty good to me. And they are starting to understand you can't build airports. This is the Department of Energy. You see this? They're showing all these new different types of accelerators, but then they get down to the bottom and they say this is really the way to go. He says we got to change from building more. We got to change to building more airplanes as opposed to building more airports. They're building huge things that they can't move them, and you got to source them and all this stuff. This is what you need: more airplanes. You can fly around. You can put that in an airplane and fly an airplane with that. I'm telling you, there's nothing you can't do with this. And it can be scaled up. This is not, it doesn't have to be this small. But for something like this, you should be able to, it should be just like a good heavy-duty generator, I would think. You know, get little people with some technical ability and some equipment, some milling machines and some, you know, focusing this and that, and some, you know, ability to work with transition metals, which are these perovskites, which are, you know, different states of energy, which will absorb different states of light, and then pump them down. Where is it? Here it is. And we would build a little device just like this and put it into here. And a zillion of these little lasers in there. And then with the panel in the back, that's going to absorb all that white, literally fluid. It's literally just like fluid that's pushing it through there. And it'll drive it right down into the battery through a photodiode. And it's going to be slapping it. Okay, so listen to this. This is a pulsation. And we can vary how pulsed it is and so forth, and the different intensities of the light and all of that stuff. So boom, 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 boom. The white can't get back out. It's got to go through here. It's just getting slapped through here, and it's just going to push down in here. Boom. And tries to get back, can't get back. Boom. Can't get back. Boom. Can't get back. Boom. Charge up your batteries. That's what you're doing right now. That's exactly what happens in a charger. You're pushing white down into the battery. The battery does not get heavy. It just gets charged up. You use all the electricity out, it's still basically the same exact weight. That's because this has virtually no weight whatsoever, and I also have shown that in the atomic bomb blast. Very obvious to see. All right, let me try to explain something. Nobody's ever understood this, and I did not understand it. I was very confused. I thought the black and the white could not separate. You had to have a dipole, and they couldn't separate. Well, they absolutely can separate, and we separated them. Now, this is what they see at Fermilab and CERN and so forth. They see these two particles, but they see them as a zoo of particles. So they just see them, and they say, well, these are the smallest ones we've ever seen. Well, this is because they are part of light. Two of them back to back make light. One of them is like an unstable particle, and the white can separate from the black very easily. Down at this range, there is no more bar magnet type of effect where you break a bar magnet in half, you have two bar magnets. You break this in half and you just got one of the white and one of the black. And I didn't realize you could do it, but you obviously can, because this is the white particle. I mean, this is the particles of light. And this is where it comes sizzling down here as we accelerate it. That's acceleration. I don't care what anybody says. They can say that's just mimicking acceleration. No, that is acceleration. That is where they divided and created fission, and that's where they came back. And here is the fission, the black separated from the white. There's no way to see. This is exactly what happened. And it's exactly what they say happens when you separate the sterile muon from the electron shower. And they also say if this can be done, it alters physics completely. Physics is the standard model doesn't work, and it doesn't. Dipole electron flood theory is what does work. Everything's dipoles, and every proton is made of approximately, my calculation is about 1,823 electrons, dipoles, 1,823 of these. All right, all globbed together. And the dark would go to the center, and the white would crust around it, because the dark doesn't matter. That'll go right on top of each other. Couldn't care less. But it will suck the white to it like absolutely unbelievable. And that's what electricity is suction. It's the white is being sucked to the black. That's what it is. Electricity sucks. You see, here's the academic denial, which inevitably comes when you bring out something that trumps what they're saying. Here's what they're saying. Most fascinating aspect of these quasi-particles is what I'm showing you, these white particles, is their ability to move in ways that would be disallowed by the laws of physics governing individual particles, says the physicist, so forth. The flexibility is enormous. Well, yes, because we can regulate, anyway, even though each electron, and I showed you what an electron is, it's a white glowy part, is performing relatively simple movements. The total radiation from all the electrons can mimic that of a particle moving faster than light. No. I showed you the single proton. They say no. They say it's not moving faster than light or an oscillating particle. It is supposed to do both. It's an oscillating particle, and it is moving faster than the speed of light, even though there isn't a single electron locally that's faster than light or an oscillating electron. That's just wrong. That's just totally wrong. Not correct whatsoever. They have to see what I present. Now, they're looking for super radiance, an ultra bright beam of photons produced by a collection of particles working in sync. Precisely what I'm showing. That's what these quasi-particles are. And they can be created for super radiance. Super radiance means you have increased the energy level. If you look up luminosity, the higher the luminosity, the higher the energy. We started out here. This is just almost no energy at all. It's just the brightness is the energy, and when you hit white like that, you can see it exploding here. That's energy pushing back. These are all being pushed back against. This one's being sucked forward, but when it hits here, it pushes back against all these. That's why you don't even see these waves. They don't have enough energy. That wouldn't have enough energy to be seen until it fell into the vortex of the Venturi. Once it hit that vortex of the Venturi, gone. And it pulled itself right out of its own magnetic wave. And when it exploded there, and it's just a continuous explosion. We don't have to stop this. We run this all day long. This backwards reverse electromagnetic force, electromagnetic field, and you can see it right here. All right, you see those backwards waves? You see how far back these things penetrate? Look at those. They're going backwards against the forward coming light. And right there is just a staggering increase in energy, because it's a staggering increase in luminosity, which is energy. And in this case, it is raw electrons separated from their black counterpart, supposedly increasing the value of them millions of times. Let me just read you what they have to say here. Say particle accelerators can fit inside a building are much less powerful than those like the LINEAC coherent light source in California, the size of a small town. Its lengthy electron racetrack is capable of emitting highly energetic waves of light in the X-ray spectrum. There has been progress made towards miniaturizing particle accelerators, particularly when it comes to devices that accelerate charged particles or plasma. That is my realm. A team of international researchers use computer simulations. We don't simulate anything. We use the real thing to demonstrate how these compact plasma, which is that white stuff, accelerators could produce bright light equivalent to that created by large particle accelerators, which is CERN, Fermilab, Lawrence Livermore, JPL, all these people are doing all this stuff. The trick was understanding how the plasma accelerators generate the quasi-particles. Why does it happen? I know exactly why it happens. I can tell you why. I say the quasi-particles are coherent systems. That is lasers, basically, coherent light, that can emerge when mediums are disturbed or excited. That just means when you create Cherenkov radiation, you go through heavy water or something like that, or into a fog. It changes things. And I can show all of these things. So they emerge, these quasi-particles emerge. Though formed as a group effort, they can be treated like discrete particles, and I can show you they are discrete particles, as they have stable properties like charge, mass, energy, size, shape, and momentum. Yes, I agree. Because quasi-particles can be created through the coordinated motion of a collection of light-emitting pulses, pulse lasers, moving through a medium. I don't care what the medium is. We're moving through a Venturi. That's the key. They can slip through loopholes in the laws of physics that would otherwise constrain more ordinary particles. In other words, broke the laws of physics, showing that electron flood theory is creating fission and fusion of light. And this is, we've been doing this, like I say, for 8 years. It's time to pay attention to this, because this could be walking around free energy. If you can increase the energy value by separating those particles, which you absolutely can, we did add no extra energy whatsoever, none, zero, and the stuff could fit in here and be probably cheaper than your cell phone. All right, and it would create this kind of energy. And that kind of energy right there, my friends, is what you pump down into your batteries. I don't care if it's a car or it's a house making electricity, or it's an airplane or a boat, or I don't care what it is. Lights, water pumps, whatever. And you carry around like that, and you plug anything you want into there, and you could just have a little whichever type of electricity you want. And this is the way to go. This is absolutely the way to, well, at least it should be looked into. Let's put it that way. And they are looking into it now, but these things go at a snail's pace. It's crazy to just sit around and hope for the best here, when we should have somebody paying some attention that has some resources. I have no resources. Zero. None. I can't do any of this. We did this for a couple of $100. I'm serious. It was a Galaxy S3 Samsung cell phone that took all these pictures, and they are stunning. Look at this. Look at this. This is these white particles coming through here. And you see how they're saying you could treat them as a single particle? Yes, you can. You see that? That is hitting and creating a Higgs field. You see it making a circle like this? And they're all doing that. and they come out and they create these circular patterns, which are Higgs fields. That's what's creating them. And the particle itself, there has to be a particle there, but it's not much. It appears that it sits on the outside rim and forces some kind of compression to the inside to show up as these fields. But I don't think there's all kinds of particles here. I think the only particle is this one on the outside. Can you see that close? Hold on. You see that little spritzer? Hitting right on the outside edge of that, and I believe that's what's making that particle spin. And they're all hitting something, and they're all making somebody spin. And that's what Higgs fields are. Now, we had one that went backwards and made a reverse spinner. And then it actually interacted with a forward spinner and ripped the particle right off. Very, very strange event. So don't forget, I just showed you those little spritzers. That's these things. Here's where this is happening, right here. Where they're coming back together as a Higgs field, and then they just become normal photons of light after that. But they come right back together instantaneously. And this was the acceleration phase. That's this right here, where they break apart and where they come back together. And it is the same exact identical particles they see at the big colliders as the smallest particle. That's what they're looking for, is the smallest particle. And there they are. Yes, absolutely, I agree. And the black one never changes size. It's a bowling ball. The white one gets big and small and turns into a shower. And they actually say this is exactly what I say. And they also claim that if we can show a sterile muon from a sterile electron shower, we have changed physics. And and the standard model has to change. And there it is right there. And this is fission, and that's fusion in the subatomic realm, which is a little different. I'll give them a little wiggle room on this, because they're using protons. But their proton, which they don't realize, is nothing more than these in a bigger ball. All right, there's zones of stability. And the zones of all stability are basically the periodic chart. And all these are is bigger and bigger and bigger balls of these particles. Hydrogen starts at about 1825 or so, and then you go up to helium, so it's like 7,000 something, and they go up like to literally hundreds of thousands of particles make these stable elements. And there's zones of stability. So if you add, and they seem to work out to be somewhere around a proton's zone, which is the smallest one that exists. So these are like the building block of elements. And the more you get of these, the bigger the actual molecule is. Now, you can make them change with chemistry and fire and everything else. You can drive off electrons and drop these and down in nuclear. You can break these apart where they'll come apart. And that's what they want, is fission and fusion. But when you do that, you create big, heavy chunks like this. They go flying off, and it hits you, you're going to get hurt. We're down here, you can't get hurt. I mean, if you put your eyeball right in there, maybe, yes. But by the time it hits out here, it's all over. There's no more problem. And we should be able to squirt it down so it never goes anywhere. Right here, it gets captured. I mean, that'd be just so close, it'd be unbelievable. It'd be a thin film of foil that would have all these different transition metals in a very thin layer. And when that hit it, and they'd have to be in a certain sequence, it would hit it and absorb this one, then absorb that one, then absorb this one, then absorb that really powerful one, and then a really, really powerful. And that's what they do, which is nothing more than light being absorbed in different frequencies. There's nothing, well, bouncing in different frequencies. That's why the same light is hitting this, that's hitting all this stuff. Why does everything have different colors? It's because that same light is bouncing back at a different frequency. And that's because every one of these colors has a different absorption and repulsion effect. That's all it is. And that's all we want to do, is have them all absorb. And then and they slap it and slap it and slap it, and it has to go in there. They go in, they go in, they go in. Where are they going to go? They have to go down into your battery. And they have no weight to them whatsoever. It almost seems like almost like you're squirting in, you know, smoke or something. I mean, that's, well, I'll show you the atomic bomb blast. It makes it very, very simple. You can understand it totally, very, very easy. The atomic bomb blast, and I'll show you a picture that we have from light that simulates that, and then we'll watch the bomb blast. All right, you see that? That simulates an atomic bomb blast. This is in the subatomic realm, but it's virtually identical. There's no difference whatsoever. You see the black particles here? That's what's going to happen in the atomic bomb blast. There's going to be a black set pushing a white set. The white, as it has to force its way through everything else, they push back against it. So you end up with this, and then the white, it just burns everything up, and then a little while later the black comes along and knocks the house down, because the black is the only thing that has mass. The white has literally no mass that I can see, or almost none. It's got to have some, but not much. All right, what you're going to see is a house burn up, just burn and smoke up like it's smoked, just like it vaporized, and then the black thing will hit and slam it like that. Preceding all this is what they call a Whistler wave, which comes out preceding the atomic bomb blast. And that's this little, and you can actually hear it. It's audible. It's in this frequency wavelength is not like light. This is in the audible range, and you can hear, and I have an example of that as well. So let's look at those two things. The Whistler wave is the first part of the atomic bomb blast, which is right here. And it goes, and then this sweeps out, the black pushing the white, forcing the white to burn everything up in front of it, but it doesn't push. So as far as I'm concerned, there's no mass here to speak of, but there's a lot of burn, and then the black is the mass. Let's watch this actually happen. All right, listen to this. This is from atomcentral.com. Very, very good. Now, here's what's going to happen. They're going to set off an atomic bomb. All right, and they are, I think they're 3 miles, 6 miles, I can't remember, but they're quite a ways back from watching. So they're observing from a distance. And what you're going to see is the bomb go off in a mushroom cloud. But listen to what you hear. This is the key. Listen to this. Did you hear that? That is the Whistler wave. It's in the audible range, which is a very long frequency compared to very short where light is. Now, the wave is sweeping across. I won't watch the whole wave. Let's come way out to here. Where are we? All right, now the wave is almost hitting us by now. So listen now. Now all of a sudden we're going to get whacked. Oh my God, scared the hell out of me. Now listen to the after effect. This is the atomic wind. That is heavy duty wind, major wind, and the house is gone. All right, this is atomcentral.com again. Now I showed you the Whistler wave, and I showed you what I consider to be the white particles hitting first and burning everything, and then the black which pushed it. Now, and I also claim the white has no mass. It has no real mass to it. And this is the proof of it. If you watch this house, it will just vaporize. The wiring, the poles, everything will just smoke. There'll be smoke just like right around it. And it's not moving. It's not like a wind. It's just vaporizing. And that is that white component. And it has no mass to speak of, but it's the same thing as like in your battery. It does a ton of work, but it has no mass to it. So when you pick up your battery, it still weighs the same amount, even though you got a nuclear bomb in there. Okay, I've shown this many times, but watch the wires, the poles, the shingles, the face of the house. As it gets radiated, it just smokes, just like glows. It just vaporizes. Now, the air and the atmosphere will be completely saturated with electrons, and then you'll see these just burning up, and then the next thing, the house will go flying. Here goes. All right, I have it running on very slow speed. So now here's the blast. There's nothing moving. Look, I'm going to stop it right here. You see the poles? You see the wires? You see the house? You see there's nothing even moving. It's just being irradiated, and the first thing was the glow, and now the smoke. All right, they can't absorb those electrons. They can't take in those fields, and those fields have no mass. They're not pushing anything. Now watch what happens now. Everything just smokes up, smokes up, smokes up, smokes up, until everything combustible basically is gone. Look, they're still there. Now everything goes flying. All right, that's what an atomic bomb was, and that's what I showed you with the white and the black particles. And the black was pushing the white. It's the exact same thing we just saw. And the Whistler wave was also the same thing. So what you just saw was an atomic bomb. Ours is subatomic. Same thing. This is a Whistler wave, so if you're way out here, you hear that. This is the black part. It's going to come and hit you sooner or later. But in the meantime, you're just being burnt and fried up into just dust. And then the black comes and knocks you down. Identical to what you see here. There's no difference whatsoever. Zero. And these are in the very long frequency. These are in the short frequency. See the difference? Okay, I showed you one of the most luminous events you could possibly imagine. And luminosity is the amount of energy an object gives off per unit of time. The amount of energy an object gives off. Now, it doesn't have to be an object. It can be a reaction. This quantity is often given in units of joules per second, otherwise known as watts. This is the same unit that's used in electric circuits, but in the form of radiated energy rather than electric power. Now, luminosity is radiated energy, but if you can grab a hold of that, you can turn it right into electric power. And that's what I'm proposing we do, and do it on a very, very simple scale, portable, in a device like this. Okay, my friends, let's wrap this up. I'm going to just go through the whole thing real quickly because I think there's a few things I didn't show you. But we started out with just a normal light wave. Then we accelerated that light wave and created the fission and fusion. I showed you how the black pushes the white, and it created the atomic bomb effect with the Whistler waves in front. I showed you what they claim is the muon, sterile muon electron showers, which changes physics, which we did, fission and fusion. Now again, this is on the subatomic level. A little bit different than what they're doing when they're colliding protons. This is what they get. It's just a big mess of stuff. We, as you saw, can direct our photons exactly where we want them, right into a collector and then down into a harvester. I hope. That's what I would hope for, because this is nothing more than light on steroids, and that is what you collect on a solar panel. You're just collecting light, but you're not getting it like this. This is just nothing but light, and so it's being pulsed, slapped through there. This is a whole game changer. All right, so don't forget, this is Higgs, and I mean, these are the Higgs fields created at Large Hadron Collider, Fermilab, and all of them, where they smash huge particles and they just get all this debris. I think I showed you this before, but I just want you to understand, that's what they're looking at, just going flying in chunks and little bits and pieces and middle-sized pieces and all that. Now, we totally, completely, 100% separated the white from the black, and here's the reattachment point. I think I showed you this in pretty good detail before. Now, so there's that. There's the Dirac, which is, everything's made out of, we live in a Dirac sea, in a sea of Dirac particles. They're everywhere, everywhere. And again, this is the photons, and this is the neutrino phase, photon phase, and explosion phase. And the same thing with the green. The green is just much more energetic, same particle. And same neutrinos. The blue is just too fast to do much with. It's just, as it comes through the Venturi, it's just sizzling. And it's just starting to slow down. And so you can see it's spinning. It's drifting to the left, spinning to the right, but you see how compacted here is? It's separated here. That's slowing down. Light slows down, so we have no idea where we are in the universe, because they use the speed of light as a universal constant. There is nothing but fields in space. And I can show you that also, and I will in a second. So far this is everything. This is light spinning. I think I showed you that, maybe I didn't. And this is the interference patterns, because they don't want anybody next to each other. They set up this, and they have these interference lines between them. That's pushing and shoving of the fields. It has nothing to do with a flapping wave like this and that. This is single slit. So that's all shown to be not correct. What didn't I show you? I think I showed you all this stuff. And like they say right here, look at this. Fission and fusion are two physical processes that produce massive amounts of energy from atoms. Millions of times the amount of energy that you would get without fission. That's what they're claiming. Those aren't my words. See, this is the Department of Energy. Fission and fusion, two physical processes, produce massive amounts of energy from atoms. Again, we're in the subatomic, but still, there should be much difference. They yield millions of times more energy than other sources through nuclear reactions. We are in a subnucleus, but it's nuclear, it's still nuclear, because anytime you're down in this range, you're in the nucleus. So that's a nuclear reaction. Only we're using just one light particle. We're not using, what they're using is these big balls and slam them together and creating fission. All right, so that's fission. When they come back together, that's fusion. But they're using huge ones. And then there's going to be a bunch of particles released. We're using just one particle at a time, so we're splitting every single one of these particles. We're not just splitting a few of them. And that's what they're doing. They're just splitting a few out of billions, because they're literally probably billions of times more particles than we have. And so we're splitting every single one. They're only splitting a handful of them, basically, compared to what we're doing. But we're doing it on the microscopic scale. So they're trying to do it on this massive scale, which is like building an airport, when we want to build little helicopters and drones now. That would be a drone compared to what they have. And that's what the Department of Energy says. We should be building airplanes instead of airports, basically, in the energy sector. It's just, you know, it's a comparison. So instead of building huge energy factories, we build little tiny portable devices like this. If you can get a yield of millions of times of the energy using these nuclear reactions, and that's what we have, a nuclear reaction, I think we're good to go. But somebody's got to jump in and take the reins of this. I have no resources to do this. And because of the way that anybody outside of the establishment is reacted to, there's just nothing, you can't get anywhere. And I haven't been able to, you know, somebody like Elon Musk, I would think somebody would want to look into this. Now, this is not a big thing for me as far as money goes. That's not my point. I'd like to see somebody save the world, to be honest with you. But I think it's a little late in the game for that. Maybe 8 years ago, when I first discovered this and made that proposition, it maybe could have been done, but I don't think so now. It's the weather. It's such a decline in such a rapid amount of time. I don't see coming out of this, but I guess anything's possible. But if we don't do something pretty quick, I don't see it. The Earth is collapsing. Water's not fit to drink. There's all kinds of catastrophes with the scrubbing of the atmosphere, because it's so compact. You know, we've blown it up so much with all this expansion of gases. That's what the problem is. The ionosphere, way outside. You see this? This is our problem. Way out here is the outside envelope of our gases. Well, we're getting dragged through the Milky Way, we're spinning on our axis, we're spinning around the sun, where there's so much interaction with that ionosphere that it's 3,600 degrees out there. 3,600. 3,600 degrees. Why? It's because our layer of particles, which is our atmosphere, has to scrub. And it's pushing everybody else, just like I showed in that red wave pushing through. We're nothing more than a particle in space pushing through fields in space, and I will show you that. The sun has the same issue. The sun is only 10,000 on its surface, 10,000 degrees. Out here, it's millions of degrees. So the surface here, 10,000. Why millions out here? Same thing. Its atmosphere, basically, is scrubbing through the particles in space, but it's so big that its scrub is enormous, so it gets millions. We only get 3,600, but there's no other reason for this. They can't explain that whatsoever, no reason whatsoever. And all of those particles are drifting into space, causing what they call a quantum foam. They're blinking on and off continuously, but you just see it as a little bit glow in the background, because they're just banging into each other instantly and they're gone. It's not like some big glob hitting something. Although they do see that. They see planets colliding together and big globs hitting each other. But normally it's just this cloud of tiny, tiny, tiny little particle interactions that are instantaneous. You know, this is a good time to show you about the way light spins. You see I put these little springy looking things? That's spinning fast. That's going to create blue or green somewhere around there. This is slower. This will be in the red. This is extremely slow from the moon because it's a re-radiation, so you only get the nighttime glow of the moon. And sometimes it can be pretty bright, but it's never going to give you that extremely high energy. Now, here's what's coming from the sun. Some of these particles are little bitty particles, just like dipoles. Yes, absolutely. Some of them are just the white, some of them are just the black. I believe that's true because they can split. I know they can split. So some of them are going to be chunks, half of this, a third of this, 10 of these, 5 of these, but they're being thrown off into space, and as they can congeal, but I think normally they oppose each other in the medium of space. But it's absolutely not empty in a vacuum, absolutely not. And even Fermilab admits that. They say it's a quantum foam of writhing particles that are interacting like foam on a root beer. Continuously frenzy of particle interactions, and that's true. Because every one of these particles is hitting something else in front of it. And that's why you see this little glow. And even John Glenn, when he went up, he said he could see fireflies coming around the edge here and looking back as here. Because the light would be hitting it like in a barn and be lighting up all these particles right on the edge. And he could see it just in the sunlight as he was leaving and just as he was coming around the other way as the sunlight was. He was in the dark and looking into the sunlight. That's the key. And he could see all these, they call them fireflies. So these are the particles coming from the sun. And they're interacting and winking like on and off. All right, so, and we're scrubbing through them. That's why we're so hot on our surface out here. And that's the dome around the Earth. If you want to call it the firmament, call it the firmament. But the Earth is a globe and is covered by that ball of gases. And that ball of gases has really almost like a firm edge to it, which has to plow through everything in front. And that's why, as I showed you before, the red. All right, you see this? Think of this as the Earth. And our atmosphere is out here. And we're plowing and spinning and doing all these things and creating a hell of a lot of heat way out at this edge. It's literally identical to this. And let me show you something else. All right, so as you know, I like to do a lot of things at one time, which I have. We're talking about light, we're talking about energy, we're talking about pretty much the origin of the solar system and how fast the magnetic fields in space and light slows down. So really we're kind of lost in space. Light has to come through these fields. You see this? These are the fields that are in space. This is actually a picture of space, and they are all dipoles too. This is a planet, I don't know what it is, which one, and this is the moon, and the moon is not spinning, so it has a compressed side and it has a stretched side. It's moving this way, it appears to me, and it also has some glowy spots on it, which indicates there's energy going on there. I don't know what it's doing, but there's some energy going on, and these are all, everything's a dipole and everything has fields. And it appears to be going this way, and the fields are being pulled back this way as we move this way, because the blue indicates it's crushing forward. All right, and everything else is rolling off this way. You see it? Rolling out that way, rolling off this way. So this is the flow going this way. Okay, my friends, I said we are basically lost in space. That's because we are. What is this? This is all of the magnetic fields that surround all of the particles that are spinning and their electrons in their ionospheres, which are, I don't care if you call it the corona, the ionosphere, it is loaded with these electrons, and they're scrubbing through space, creating a generator effect, which creates the polar effect on the planets. And this one doesn't have a polar effect, the moon, because it's not spinning. They have to be spinning. This one's crushing its light. I think I talked about this before. But here's the very interesting, well, there's a lot of interesting things here. Everything's a dipole. You see them? They're black and white, black and white, black and white, black and white, everywhere. And they all create these magnetic fields. You see fields everywhere. Field, field, field. They all have a field. So when light comes through that, it slows down. Don't tell me it doesn't. It has to. Absolute no other alternative. So we have no way of knowing where we are right now, because there's going to be denser areas and thinner areas, and you can see that on the arms of the Milky Way, which I guess I'll have to show you. This is, I don't know what that looks like a pyramid. I'm telling you, and I found things on Earth that look to be not from this Earth. And what is this? I don't know. I have no idea. But I can tell you what, these things here on the moon are energy. That's energy. That's energy. That's energy. There's energy going on there. And this, I don't know what's going on here. And that, heck, yikes. That looks like Atlantis. And this looks like a pyramid. And things look like they're going back and forth. I'm telling you, this is the kind of stuff. This is Dylan Carpenter sent me these pictures. He just took them with his cell phone. Now this is the same as the one I just showed you, the other one. That one's a real close-up, and this is further away. And this is, I don't know what, this could be, I don't know what. It could be Venus. I think he sent me one, and I think it's Venus because it has a double field. Let me look into that in a second. But you can see it's a similar. The blue is everything's going this way, but he really focused in on the other one, and you can see the details of. I don't know what it is. I have no idea. Yeah, here it is right here. I think this could be Venus, but that's just a guess. But you see the field coming out around here, these nice even fields coming out around, and they have like a really shudder to them, like a, and that's it. That's their field that surrounds them as they move through the atmosphere of space, which is an atmosphere. It's not vacant by any means whatsoever. As they move through that, they create a wake and a field. And I showed you, here it is right here. These are them. Now, this is a secondary field. You see that field stops here, the nice heavy-duty one? And then there's another one out here. You see it way out here? And it's kind of weak looking, but it goes right down the same polarity. That's not coincidence, I don't think. I think this is spinning in reverse and moving forward. And the only one close enough to have this effect to us would be Venus. So if it was spinning backwards and moving forward, spinning around the sun, but going backwards on its axis, which it is, would it create those two fields? It might. But there's definitely two fields converging into one as far as I'm concerned. You see the two of them right there? They're both meeting together in that dipole. And that dipole is a little bit different. If you look at it real close, it's got a secondary, it's got like, I got a white brilliant and then a white not so brilliant. And I don't think that's normal. Whoops, here it is right there, you see it? I do not think that is normal. And I have other ones showing that Venus has a strange interaction with the particles that are hitting it. And I've heard, I don't know if this is true or not, but I think they say that it might be hotter on the dark side of Venus than it is on the light side. And I think I can understand that because of its reverse spin. I think I might be able to, I'm looking at it, I'm trying to figure it out, because if it's true, that's very, very strange. But Venus is a strange character. It's going backwards and moving forwards through the solar system like we are, only instead of spinning where it's rolling down, like rolling down the road, it's spinning backwards. So it's going this way, and it's like spinning the tires backwards going down the road. It creates a crazy field and a lot of heat and all that stuff. Now look at this. I found this as strange can be. Here, this is Earth. All right, they are talking about this particle that came across here, which looked like a spaceship, and we shot out some kind of a blast of radiation. Now, whether it was just pulled towards it because of the magnetic field, or whether something blasted it, I have no idea. But this is what I found very, very interesting. This is the sun. All of this stuff is coming. This is Venus. Now look at this. What's facing the sun should have the most energy. It should be the brightest. As we're facing the sun, it should be lit up. Look at what's going on here. The dark side is facing the sun. The bright side is facing away to the sun. Like I said, I heard somewhere that this was the case, that this side had most of the heat, just like we have heat right here during the day, and there's the night in the back, and there's no real heat to speak of. And then this is very strange too. But I do think I understand it. This is the wraparound where they're banging together, and at that point, somehow it's creating a void of, I don't know. But you should think you could see through that and see more stars, because these should be the stars and things that are in the sky that are glowing, right? But anyway, this is the thing to key off on. Look at that. You see it's got black and white, and then black on this side and white on this side. It's like, is it because it's going backwards, spinning backwards, when it should be spinning in one direction, and we're spinning the correct way? So, because this thing here is putting out heat like crazy. We're, let's say, 100 degrees or so, central temperature around the Earth. This is like 800 or 900 degrees. And it's not because it's a lot closer to the sun. It's because of this scrub reverse through the particles in space. All these particles in space, it has to get through them. I found that very, very interesting. All right, so basically that's what's right up above us in space here. And again, we have no idea how far these things are, because the particles of light, which we always expected just keep going exactly the same speed, obviously do not. No way in the world could they go the same speed. So there's dense spots and less dense spots in our traveling through the galaxy. All right, planet Earth is somewhere out here on one of these arms of the Milky Way, and it's spinning in this way and concussing all the particles that are in front of it, so it's bending the arms back. Now, if we are in a dense area, we're going to scrub harder. If we're in a blank area, we're going to scrub less. So there is that factor to take into account. Don't forget now, these are all the particles that will be given off by the sun. This is a total eclipse of the sun. So this is the moon shadowing the disk of the sun, so we can see the radiation. You see these three red spots here? Let me focus in a little better on that. You see those three red spots? The sun is going this direction, and it's spinning in this direction. And the reason I know that is because the scrub zones are here. It's got to be going this way, and it's got to be spinning in this direction. So its atmosphere is scrubbing on top of going forward. It's scrubbing this way, creating these bubbles and so on. This is the trailing edge. You see it trailing away? You see that trailing and trailing? And you don't see these big heavy-duty impacts? Again, the sun is going this direction, spinning that way. And that's why we see these right in this particular spots. Otherwise, you see them even over here as well. All right, this is all the stuff that's coming off the sun, and we have to plow through this, and it creates its own polar field. You see it? Yeah, the sun, and of course, again, this is the moon disking the sun, so we can see everything that's happening in the back. Extreme energetic reaction because of the spin and the forward motion. That's the only reason you could possibly do that. I'm a material scientist. I don't just guess at this stuff. This is where you can see it. If you take your time and look, you can see these things. You see, this is pretty accurate. They're talking about ionized, negative ions, high. This is the ionosphere. Ionosphere. And the same thing with the sun, it has a corona. It's identical, only that one there is really intense because of all that particles we were seeing going off. We don't spit that stuff out. That's why this is so intense. Millions of degrees out here versus 10,000 on the surface. We've got, let's say, 100 on the surface, but still 3,600 out there because of the scrub. And they have this, we all have the same scrub. Now I'm going to show you how we funnel through the arm of the Milky Way. All right, take your time and pay attention to this. Remember I showed you how we're on the arm of the Milky Way and it's spinning around and around and around. Well, it takes a very long time for that to spin around. So we're just, I don't know what we're doing, to be honest with you, but we're moving on one of those arms. It's pretty apparent to me that that's correct. Now, in that case, all of the mass, the major mass is going to be forward and the other masses will follow behind. And they are spinning in a right-hand rule, it's called. Now, again, the sun is scrubbing against these incoming particles and ripping off some of its particles. That's what those 3 red spots were. Now, they're showing it here. I would suspect, well, I guess it's probably going to be right in this area where the main scrub is, because it's spinning too. We're all spinning. And we're not only spinning around the sun, we're spinning on our axis as well. And they all are. Now Venus is going with, just like this with everybody else, but its spin is backwards. All the other ones are like rolling down a street. This Venus is going this direction, but its tires are going backwards. Basically, you have to think about it that way, and that creates that 800-900 temperature, you know, of its surface. It's just, you know, its atmosphere, its surface, whatever you want to call it. And we have an ionosphere that's 3,700 degrees, and that's because we're scrubbing as well. We're all scrubbing. This is nothing but saturated with those particles that I showed you, which are these fields. There's not only these particles, but then there's all the fields. These fields, they don't take any account of this. Like, it's not even supposed to be there. They're everywhere. They are everywhere, everywhere, everywhere. Everywhere. There is nowhere that they are not there. My particles are everywhere. There is nowhere that they are not there. And there they are. And they're not that far. So you can take it from there. But I think we best beware. And that's what I got. All right. All right, I love you all. We're living in strange times, my friends. Very strange times indeed.